Now, I want you to keep in mind as we do this last topic on systems that the concepts that you would have learned in an algebra class about systems are all legit. But if you're saying, what did I learn about systems? Well, I'm going to review it with you briefly. But I think you'll say, okay, yes, I remember systems from my algebra classes. I'm going to show you a couple information slides, but I always like to show you a system so that you basically can refocus on that idea. And simply remember that a system is two or more equations that are solved simultaneously, which is really just a fancy way to say we've got these two equations, we're going to try to put them together and solve them for one solution. A system. And I say, do you remember that from algebra when you kind of like group equations? So in a moment, we'll solve 5 sine and 5 minus 5 sine. In a moment, we'll solve that. Let me give you a couple refresher concepts. And in all honesty, you can just read them, or you can read them and jot them down. It's up to you. Some of you, though, should say that, oh yeah, I saw this same thing in algebra, even in Algebra 2. Because anytime you have a system of equations, the solution is always going to be the intersection. Does that sound familiar? If it does, again, you don't need to write it down, or you can just paraphrase it, or you can jot it down. A solution is always the intersection. Now, in Alg 1 and Alg 2, you were just graphing some straight lines, right? You were graphing straight lines, and the intersection was like a point. But think about what's going to happen in this polar chapter. We're not just graphing straight lines. We're graphing like a rose or maybe like a cardioid. Okay, we're graphing these interesting shapes. So where will these shapes intersect? It's going to be a little more fancy than just a couple straight lines. Okay, but we'll still look for the intersection. That means that the solution is going to be a point. Again, you might say, yeah, I know that, Mr. Naylor, that sounds good, but you can always remind yourself. So the solution is a point or points. Maybe there'll be more than one point. And then we have this last kind of fundamental idea that if it's going to be a solution, then it has to be a solution for all the equations. Now, it's funny, that concept people will often say, yeah, of course, but that sometimes ends up being the reason that we don't get the answer right because, well, I'll tell you that we have to check the answer. We have to check the answer to make sure that it actually works in all the equations. All right. We're going to actually solve this system two different ways. We're going to solve it graphically, and then we're also going to solve it algebraically. If you're already wondering, do I need to be able to do it both ways? I'll say that you're going to need to understand both ways. At some point, you'll be able to decide, and you'll be able to say, I'm just going to do it this way, or I'm going to solve it, again, either graphically or algebraically. Okay, but let's solve it graphically first. That's what the Desmos is all about. I hope that you can play along and use Desmos. Of course, if you just want to watch me, you can watch, but it's usually better if you participate. Honestly, we're just going to type it in, so you can get a little jump on that whenever you're ready. You can just type in the two equations. Remember some of the things that are helpful with Desmos. The settings should be set so that it's in polar and also degrees. Polar and degrees. Now, when you type 5 sine of theta, I'd like to say that you shouldn't be that surprised that you get a circle. On the test on Friday, you'll have to have knowledge that 5 sine of theta was going to be a circle. How will you have that knowledge? You'll have to study a little bit. How about 5 minus 5 sine of theta? Are you surprised that that comes out to be a cardioid? If you are surprised, then again, you'll have to study a little bit, okay? Because when you have 5 and another 5, it's always going to get you that cardioid shape. Now, some of this is just visual. And honestly, sometimes people don't like this because it's like, I want some like numbers, Mr. Naylor. But right now, all we really can do, now we could zoom in. I'm trying to zoom in. We could zoom in, but all we really can do here is look at this graph and see that the points, or at least a point of intersection, is right here in the middle at 0, 0. Okay. How about this point right here? Now, that's not on 0 degrees, rather it's on 30 degrees. Okay. But what's the value of R? What's the value of R? Let me back up a second here. We had 0, 0, so we're just going to list it. Now we're kind of moving over to this next point. As I said, a lot of this is visual, so you're just looking at this. It looks like it's on 30 degrees. And by the way, I'm not going to give you one that's some really weird answer. So yes, it's 30 degrees. Now the R value looks like it's halfway between. It looks like it's halfway between 2 and 3 if you just kind of use the circles. So because I'm not going to give you one that's really weird, I would say a half is about as weird as it'll get. Then we can sort of be confident that that's going to be at 2.5, 30. So then we rotate over here. Okay, and again, remember what you guys learned the very first day. That's a point. It's got a radius and it's got an angle. The angle looks like it's $1.50. The radius, once again, looks like it's at 2.5. So we're making a list of points. And just so you guys realize, it's clear that there's more than one point. I know that's pretty obvious, but there's more than one point. As I rotate back around, it could be argued that point back in the middle could also happen with 180. Excuse me, with a 0, 180. Basically, the argument here is that I rotated around 180 degrees. There's no reason that that can't also be given as another point. In fact, I guess if I actually rotated the whole way around, my mistake, I apologize. If I rotated the whole way around, that would be 360. Okay, so there's kind of two ways to describe that point in the middle. Now, here's the part that sometimes can be a little sketchy. People are kind of like, really? I didn't realize that that would happen. And that is that these points need to actually work in the equations. What do I mean these points need to work in the equations? Well, if you plug in 0 degrees or 30 degrees or 150 degrees into these equations, they would have to actually come out to be the correct R value. I need to do it right here so we can see it on the camera. I'm going to plug in 150. I'm just going to kind of randomly skip to that one. That means I'm going to plug 150 in for both these equations. That'd be like the sine of 150 times 5. Now that comes out to be 2.5. That's good. When I plug 150 into the other equation, it also comes out to be 2.5. That means that it's a solution. Okay, that means it checked. Sometimes people circle it, or sometimes we just leave it alone, because now I'm going to show you what happens if you plug in 360. Now, if you plug in 360, you would have to plug it into both equations. And make sure you don't miss this. I mean, you can try it on your calculator or you can just look up here. It's not hard to do, but if I plug 360 into the second equation, it's really weird actually. It comes out to be, well, it comes out to not equal 0. It comes out to be 5, sort of like a whole different number. What that means is that this point is actually not a solution. It's not a solution because it didn't work in both equations. Now you say, but it looks like a point on my graph. Right, it looks like a point on the graph, but when you check it, it's actually not a solution. Why don't you try to check one of these 2 points? Like, try something here, make sure you can do it. Listen, all you have to do is plug in 0 degrees or 30 degrees. All you have to do is plug in theta. If you're plugging in 0 degrees and you plug it into both equations, you sort of get the same phenomenon. You end up with the point not working. But if you plug in 30 degrees, okay, now you have to plug 30 degrees into both equations, it does work. What you have to be careful about here is that you don't make too many conclusions. If you're kind of sitting there and you're like, does this happen all the time? Well, what do you mean, does it happen all the time? Okay, it's not necessarily true that you're always going to end up crossing off 2 points and keeping 2. It's not always the case that some of them work and some of them don't work. It just kind of depends on the problem. Okay, there are some problems we do where every point you list is going to work. There's not a problem that we do where you cross off all the answers. Okay, in the case of this one, we crossed off half of them. The graphing method. If I can say sort of honestly, it's not my favorite because it seems a little bit sketchy. It seems like, we get points and then we have to cross them off, but it's part of the way it goes. The algebra method, I tend personally like because it's a little more mathematical and it actually will lead you to the right answer right away. Now, the algebraic method would say that R equals something and R equals something else. Well, that means that both of these somethings would need to equal each other. That means that I could substitute one for the other. It's like a substitution method. Now, I'm sure you've heard of the substitution method. If you finished an algebra class, you would have used substitution. This is just the substitution method with some R's and thetas. Okay, so we basically make the 2 equations equal each other. Okay, now I hope that doesn't make you shudder. That's actually an equation that we would have solved in the last chapter. You guys did a nice job with it at that time. It's an equation that I kind of have to organize things. I need to kind of move numbers around. Probably the best thing to do is to move the 5 sign over with the other 5 sign. A good old kind of collecting the like terms. So now we have 10 sign equaling 5. Okay, again, this is just like an equation. You guys actually delved into these quite deeply. This particular equation is a little more basic because it turns out that I'm just going to end up with the sine of theta equaling 1/2. Now, in a normal setting, you could, on your calculator, strike one more key and have your answer. And some of you are going to do that. You're going to strike the inverse key because when you do the inverse sign, you have solved that equation. Now, I'm kind of saying it that way because there's something else that we're going to do before we strike that key. But if you already strike the key, it's fine. Some of you, you're going to do it anyway. But before we do the inverse sign, or before we just stop with that, I want you to think about some theory. Okay, now again, a little deep here, but there's theory that says that if the sine of theta equals a half, that's a statement about a y value and an r value. Now, if you're like, whoa, where'd that come from? It actually came from the unit circle, because sine is always y over r. And that means that those two numbers, 1 and 2, represent triangles that would have those dimensions. Think about this with me. If the y value is 1, that means there's a positive triangle, a positive y value. And that triangle right there has a positive y value, again, of 1. By the way, the r value is 2. And I hope that it kind of rolls off your tongue that the other dimension would be root 3, because when 1, then 2 always leads to root 3. But listen, what's important here is that you guys understand that there's another triangle that has a positive y value. And again, it's something we did back with the unit circle, probably goes back to September, but at the time you guys were really good at it. You actually really were. And that triangle right there is another positive y value because it goes up. Okay, it happens to be that it also would satisfy the 1, 2, root 3. Maybe you would put a negative on that, thinking about positive and negative. Now, there has to be something inside of you here that says, okay, Ms. Naylor, this should be headed to the same answers, right? Right. We already found the answers. Okay, but let's understand how these triangles over here lead us to those same answers. You should know that the angle across from the number 1 is 30. If you don't know that, try to get that into an important part of your brain when it comes to trigonometry. That means that this angle right here is also 30. Now, when it comes to the answers to this problem, I'm talking about the answers to this equation. The answers are actually going to be the terminal sides. The answers are going to be the rotation to the hypotenuse. Now, the rotation to that hypotenuse is 30. But it's this hypotenuse over here that we have to think, and you might just want to watch, about this rotation. Did you see how I started back at 0 and I rotated over to this hypotenuse? Okay, now that one is not 30, but it's going to involve the number 30. I hope you would say 180 minus 30 is going to give us 150. So here's what just happened. We solved this equation for 2 angles. Yes, 30 is what you got when you did the inverse 5 minutes ago. But 150 is what you get when you think about this triangle. And both of them are answers. Now, technically, both of them are going to turn into points. Even though we already did this, you would have to say that, okay, when I take 30 and plug it back into the equation, I end up with 2.5. So 2.530, it has to be a point. Same thing with the $1.50. You take a $1.50, you plug it back in. We already did it, and it comes out to be 2.5. So the answers to this problem are actually points. But it's the angles that took a little bit of math. Okay? Yeah, go ahead.
Oh, would we have to try, or would we just subtract like a different side?
So here's the answer to that is it depends. It depends on kind of what you understand. Because Chase, what if for some reason the triangles were these 2 triangles, and you say, well, when would it be those 2? Well, maybe if instead of this being sine, it was cosine. So my answer to your question is, will you know what to subtract? So if this is a cosine problem, it actually would have been the x that equaled 1. And then you'd be subtracting from 360. So again, Chase, it depends. It depends basically what you understand. And I'll give you credit for it, okay? The triangles, though, is really the theory. All right, now there's an algebra method, there's a graphing method. And what I'm going to ask you to do with this this is actually a little bit more than a homework, because what I'm trying to do is say, I want you to try to figure this out. If I just make this homework, some of you will really work on it, and some of you maybe won't work on it as much. So we're making it like just a small assignment. It's a small assignment.